In this unit, the goal is to be able to predict the trends and the properties of the elements in the periodic table. An electron configuration simply represents the distribution of the electrons among the various orbitals in the atom. The example we have here is electron configuration 1s2. In this case, the number in front represents the principal quantum number n, so in this case n equals 1. S represents the atomic orbital, which is related to the angular momentum quantum number L, so in this case L equals 0, because L equals 0 represents an s orbital. And the superscript 2 represents the number of electrons in the orbital or subshell. So in this case, the electron configuration 1s2 simply means we have 2 electrons in the 1s atomic orbital. Another way to show electron configurations is to use orbital diagrams. These are graphical representations of the electron configuration where we use a box, a circle, or a line, so a box, circle, or line, to represent an orbital. An arrow is used to represent the electron and its spin. An arrow pointing in the upward direction, spin up, represents a spin or ms value of plus 1/2. And an arrow pointing down, spin down, represents an ms value of spin minus 1/2. The starting point for this is understanding the relative energies of the atomic orbitals. For the hydrogen atom and other one-electron systems, the energies of the atomic orbitals depend only on the principal quantum number, n, which is given by the Rydberg equation, where the energy is inversely proportional to 1 divided by n squared. So we see that the 1s atomic orbital is the lowest energy atomic orbital because it has a principal quantum number of n equals 1. The next lowest energy orbitals are the 2s and 2p atomic orbitals, which have principal quantum number n equals 2. Then we have the 3s, 3p, and 3d atomic orbitals, which have a principal quantum number of n equals 3, and so on. However, for multi-electron atoms, the energies of the atomic orbitals is also determined by the angular momentum quantum number, L, in addition to the principal quantum number. So as we see in this diagram, where we've ordered the atomic orbitals from lowest energy to highest energy, we see that the 2s atomic orbital is lower in energy than the 2p atomic orbitals, despite the fact that they both have the same principal quantum number, in this case n equals 2. Similarly, the 3s atomic orbitals are lower in energy than the 3p atomic orbitals. However, interestingly, we see from this diagram that the 4s atomic orbital is lower in energy than the 3d atomic orbitals. And this is true even though the 4s atomic orbital has a higher principal quantum number, n equals 4, than the 3d atomic orbitals, which have a principal quantum number of n equals 3. So we can see that for multi-electron atoms, the energy levels are split into various sublevels of differing energy. So the s orbitals are always lower in energy than the p orbitals, which are lower in energy than the d orbitals, and the d orbitals are lower in energy than the f orbitals. So we can use this information now to write the electron configurations of atoms in the periodic table. We'll start with the first element in the periodic table, hydrogen, which only has 1 electron. Now we place the electrons in our atomic orbitals according to the Aufbau principle, which simply tells us that the electrons go in the lowest energy orbitals first and then move to the higher energy orbitals. And so the lowest energy orbital is the 1s atomic orbital, and so we would place that 1 electron from hydrogen in the 1s atomic orbital. By convention, we write that electron as an arrow pointing in the up direction. And this simply tells us that that electron has a magnetic spin quantum number, or ms, equal to plus 1/2. And sometimes this is denoted in shorthand notation as spin up. And so the electron configuration of hydrogen is therefore 1s1, which simply tells us that we have 1 electron in the 1s atomic orbital. The next element in the periodic table is helium, which has 2 electrons. And since we've already placed 1 electron in the 1s atomic orbital, we just have to place the second electron in the orbitals. Now, as you may recall, each atomic orbital can hold a maximum of 2 electrons. And so we would place the second electron also in the 1s atomic orbital. You'll notice, however, that the second electron was placed spin down, which tells us that it has a magnetic spin quantum number of spin minus a half. And this is due to the Pauli exclusion principle, which tells us that no two electrons can have exactly the same four quantum numbers. And so the first electron is always placed as spin up, or spin plus a half, and the second electron in the orbital is always placed as spin minus half, or spin down. And so the electron configuration for helium is 1s2, which tells us that there are two electrons in the 1s atomic orbital. The first electron is spin up, or spin plus a half, and the second electron is spin down, or spin minus a half. Moving along, we move to lithium, which has 3 electrons. And so in this case, the third electron has to go in another atomic orbital. And the next lowest energy atomic orbital is the 2s atomic orbital. And so lithium gets, the third electron for lithium gets placed in the 2s atomic orbital. It's spin up. And so the electron configuration for lithium is 1s2, 2s1. 2 electrons in the 1s atomic orbital, and 1 electron in the 2s atomic orbital. Moving along, the next element in the periodic table is beryllium, which has 4 electrons, and the fourth electron also is placed in the 2s atomic orbital, because again, each orbital can hold a maximum of 2 electrons, and the second electron in the 2s atomic orbital will be placed spin down, or spin minus half. And so the electron configuration for beryllium is 1s2, 2s2, or 2 electrons in the 1s atomic orbital, and 2 electrons in the 2s atomic orbital. Next, we have boron, which has 5 electrons, and in this case, the fifth electron goes in the next lowest energy atomic orbital, which is the 2p atomic orbital, and again, it gets placed spin up, or spin plus a half. And so the electron configuration for boron is 1s2, 2s2, 2p1. 2 electrons in the 1s atomic orbital, 2 electrons in the 2s atomic orbital, and 1 electron in the 2p atomic orbital. The next element is carbon, which has 6 electrons. And in this case, the 6th electron also goes into the 2p atomic orbitals. However, in this case, we have a choice. We can place the 6th electron in the same 2p atomic orbital as the first electron, in which case it would be spin down, or we can place it in one of the other 2p atomic orbitals, in which case it would be spin up. So which is the correct configuration for carbon? As it happens, this is determined by Hund's rule, which tells us that the most stable arrangement of electrons in subshells is the one with the greatest number of unpaired electrons. And since placing an electron in another orbital gives us the most unpaired electrons, this is the correct electron configuration for carbon. So we see here that carbon has an electron configuration of 1s2, 2s2, 2p2, or 2 electrons in the 1s atomic orbital, 2 electrons in the 2s atomic orbital, and 2 electrons in the 2p atomic orbitals. However, here it's important to remember that when we say we have 2 electrons in the 2p atomic orbitals, it means we have 1 electron in one 2p atomic orbital and another electron in a different 2p atomic orbital. So the spins are unpaired. The next element is nitrogen, which has 7 electrons, and again, according to Hund's rule, that 7th electron would go in the third 2p atomic orbital. So we have 3 unpaired electrons in this case. And so the electron configuration for nitrogen is 1s2, 2 electrons in the 1s atomic orbital, 2s2, 2 electrons in the 2s atomic orbital, and 2p3, 3 electrons in the 3 2p atomic orbitals, 1 in each 2p atomic orbital. Next, we take a look at oxygen, which has 8 electrons. And in this case, for the 8th electron, we actually don't have a choice. We have to start pairing the electrons. And so that 8th electron goes into one of the 2p atomic orbitals, but we pair the electrons in this case. And in doing so, we have to place that 8th electron in the spin minus half or spin down position. And so the electron configuration for oxygen is 1s2, 2s2, 2p4, or 2 electrons in the 1s atomic orbital, 2 electrons in the 2s atomic orbital, and 4 electrons in the 2p atomic orbitals. Next, we take a look at fluorine, which has 9 electrons, and in this case, that 9th electron goes in one of the other 2p atomic orbitals, again spin down, and the electron configuration for fluorine is 1s2, 2s2, 2p5. And next we have neon, which has 10 electrons, and that 10th electron now we have to pair again. And so the electron configuration for neon is 1s2, 2s2, 2p6. So here we have 2 electrons in the 1s atomic orbital, 2 electrons in the 2s atomic orbital, and 6 electrons in the 2p atomic orbitals.